Brian Greene in studio. We're listening to some U2, sir, from the Oscars last night.
And yapping over it.
And we're yapping over it because I think he has an amazing voice.
Yeah, it's good. Very melodic.
Yeah.
Well, good for him.
Brian, you watched the Oscars last night?
You know, my wife was watching. I was in the other room. I popped my head out every time she left.
So you're in the other room
then.
trying to figure out the universe,
That's
and she's trying to see what these ladies are wearing.
The Oscars.
Yeah, exactly.
Yeah, she loved it. I heard not everybody else did, but she did.
Yeah,
What were you doing? What were you doing in the other room?
Honestly, I was doing some calculations.
Oh, yeah?
I told you.
Having to do with black holes.
See, I told you.
What did you come up with?
You know, I should have watched the Oscars.
And who checks your math
You know, the math checks itself.
in the end?
Yeah, I mean, if the results don't make any sense, that's the wonder of math. It kind of slaps you in the face and says, this doesn't work. And it is self-correcting. So that's the beauty of doing equations.
No,
Tell me about it.
I disagree with your philosophy on mirror symmetry. I don't know if I'm 100% in agreement with that. Now, but before we talk about it, could you explain what it is?
Mirror symmetry.
Yeah.
You know what? Einstein taught us this amazing thing. The shape of space affects what we observe. Each shape yields different physics. What we found is, unbeknownst to Einstein, you can have two different shapes that yield exactly the same universe. And those shapes are called mirror shapes if they do that. Now for the quiz.
Okay. What does that mean? I don't know what that means.
Is there two universes?
Well, you would have thought Einstein would have looked at these two different shapes for the universe and said, these are two different universes. Clearly, period, that's it. But when we do the more refined approach to the laws of physics that we are struggling to develop, an approach called string theory, we don't know if it's right yet, but within this approach, you can have two different shapes. You look at them, they look different, but yet in a mysterious quantum mechanical way, they yield identical universes. It's like, you take a word, right? Let me take the word cat. What's that in Spanish? Gato? I don't remember my
Gato.
Spanish. Yeah, right. So you look at those two words, they look completely different. Cat and gato. But yet, they are the same thing. Secretly, there's a dictionary that takes one to the other. That's the same thing that we found, a dictionary that takes one shape to another shape, same universe. The cat.
So is that what string theory is?
String theory?
No, it's not.
No. Well, it's a part of string theory. String theory is an attempt to realize a dream, again, that Einstein had, which was to find what he called the unified theory, which would be one idea, one master equation that might describe everything.
Wow. If Einstein's number one, who's number two? Because everyone always refers to Einstein. Who was the second guy?
Well, I don't even know if he's number
respected?
one. It's a tie, I think, between him and Isaac Newton.
Okay.
I mean, Newton obviously was a long time ago, and what he did doesn't have the same kind of sophistication. We teach it, to high school kids, whereas Einstein we teach to the graduate students for the most part. But Newton was going from nothing, right? There wasn't anything before him that he was really deeply building upon. This guy just sort of looked out at the world, at the planets, the moon, and realized that the force governing the moon is the same force that governs a rock when you throw it, from here to there. Why would that be the case? That's a deep insight. It's gravity, right? But who would have thought that it's the same physics that governs up there and down here? So you kind of united the terrestrial and the extraterrestrial in a new way of thinking about how the world works.
Yeah, Einstein kind of had a head start.
Yeah.
So he really could work off of other people's work.
Now, he was still a pretty bright dude. I'm not trying to take anything away from him.
Imagine how good he would have been with a computer. He did all that shit by hand and calculated
you're
on a
absolutely right. I
blackboard.
sometimes wonder about that. If you were to go back to the great geniuses, even Galileo or Newton, or even, go further back, Pythagoras, if these guys had the computational power that we have, what would they have done?
Nothing. They'd just be looking at porn.
That's it, probably, right? The history of civilization would have been completely, in an alternate universe, right? Nothing happened. They had the computer too soon.
What are you bad at? Because you're so good at this, right? The universe, astronomy, and math, and all that. What are you bad at?
Well, if my wife is here, she's
probably got a few
list
things.
a whole bunch of things.
But where your brain is just
I've got an awful memory for faces. I meet people, and then like the next day I meet them again, and I'm like, "Hey, how you doing?" And they're like, "We spoke yesterday." I was like, "Oh,
wow."
You know, so that's constant.
Wait, is that all? Because Dr. Kaku, we've had Michio Kaku in here.
He doesn't recognize us.
Yeah. I see him all the time, and he never remembers that we've interacted. I wonder,
and he's very scared.
I will remember your face. I'm going to have it emblazoned right here.
Yeah.
But I wonder if that's because you guys are so focused on more important stuff than just people's dumb faces.
You guys don't have time for nonsense. Like, you're not watching the Oscars last night. Of course you're not.
No, but I did pop in. Yeah. I saw some of Ellen's jokes.
Okay. Pretty good. Right.
I saw the pizza. And the selfie I saw.
Yeah. Okay. That was a big story. Yeah.
Yeah.
And are you constantly thinking about like physics? Is it always like when you make a turn in your car? Are you assessing the centrifugal force? And
it's an interesting thing. At some level, yes. It's like it's always there. Because physics, many people think of it as like some subject that they were forced to take in high school, and they were so thrilled when they like finished it and they could just forget about the whole thing. But that's sort of a tragic perspective, and it hurts me when I see that that's how kids view physics. Physics is a way of understanding reality, of engaging with the world, of making sense really of your own existence in the deepest possible way.
Can I defend those students though?
Yeah, please.
It's how they taught it.
Yeah, I know.
There's got to be a better way to teach some of these tougher subjects to get you into it.
No, I agree
It just
completely.
felt like a drag when you're in that classroom.
I like real-life applications of things, too, especially in physics, because it's with you every day. You're walking in it constantly. And like when you're driving and maybe it's snowing out, you have to assess the friction on the road and your car and your speed, and you're constantly putting it in check, and that's all physics.
No, I completely agree with you. And I mean, I don't want to like go like Mr. Plugging stuff here, but one thing that we're doing right now is trying to change the way people teach physics. We have this new thing, this World Science U, that is going to go live on Thursday or so, and the whole point is to inject a whole level of visualization into these abstract ideas. I mean, you teach any kid the laws of physics, even from Newton, they're so abstract if you haven't encountered that way of thinking before.
Yeah.
But if you can turn abstract ideas into vibrant visuals, all of a sudden they make sense. I mean, I've been at a blackboard with like a piece of chalk trying to teach kids, about some of the features of, say, black holes or the slowing of time and relativity. Weird and wonderful ideas. But it's hard for them to get it, and I'm trying to scratch on the board. And you talk about what I do poorly. I am really bad as an artist. I have my kids make better diagrams than I do. But if you use the power of the digital to create real sharp visualizations of things, then I see the kids get it like in a moment. They're like, oh yeah, I see, I get it. I really can now put it in my mind. And that's what we're trying to do, to change so that that's the norm of the experience in the classroom, as opposed to the usual where you're like, oh my God, I don't get it.
Right.
What are the odds that Einstein was wrong? Like, because he was such a genius.
He was for certain wrong in some deep sense. Even Einstein himself knew that he was taking an incremental step forward, giving us a deeper understanding of space and time and gravity. But he knew that it wasn't the end of the story, because the way physics and science more generally works is people understand something in one era, and then in a later era, they expand the understanding. They typically don't wipe out what happened in the past. Newton is still with us, right? We do still teach Newton, and it's good that we do, because it's a close approximation to the truth, but Einstein did a better job, and 10, 100 years from now, somebody else is going to do a better job still.
It's very difficult to grasp the concept of space as anything more than a giant, endless void.
Yeah.
And when you talk about things like traveling from point A to point B and making it shorter distance by folding space on itself and putting those points closer together, it's hard to conceptualize it because you're not thinking of it in this two-dimensional piece of paper look.
Right.
It's like I said, a big void. And when you talk about different shapes containing the same universe, again, how do you give something a shape when, again, it's just this infinite?
Yeah, no, I understand
Very hard.
the challenge that presents, because when we think about shapes, we always think about them as a shape within space, right? You got the shape of your water bottle that you're just drinking from, the shape of my coffee cup, the shape of the microphone. They're all objects within space. When you think about space itself, it seems like, well, how can it have a shape?
Right.
It's the container. It's just like the whole thing that goes on forever. And the problem is that we have difficulty thinking in higher dimensional spaces, right? And that's why we use lower dimensional versions like the piece of paper to stand in. It's a proxy for space, if you will. Just because our brains are kind of limited in trying to grasp these ideas. And it makes perfect sense that our brains are limited. Why?
I like how you say ours. Thank you for that.
No, you know,
you mean yours.
No, I do not mean it all. This is a collective effect. And I'll tell you why. It's evolution. Right? So our forebears, when they were out there like on the savannah trying to survive, if they sat down to contemplate the shape of space, they got eaten, right? So there was no evolutionary advantage to trying to understand reality in a deep way. What you had to understand there were the very basic things like, where do I throw the rock, to hit the antelope so I get my dinner? And that's why, for instance, if I take this water bottle, right, and I throw it at you, you know where to put your hand to catch it, even though you're not doing a Newtonian calculation in your mind. You have an intuition about it, and that's evolution has impressed
upon us. You throw a bottle, he will catch it.
There you go. All right, here we go. Are you ready? Are we going to do this? We're going to do it. Here we go. And there. All right, he caught it. Just made my point. And that's why.
Very good.
That's why these ideas are so hard for us, because we're going against evolutionary pressure in trying to understand things that we didn't need to know to get the next meal. But now we kind of have the next meal right in front of us. And we're not just thinking about survival any longer, and we're trying to go deeper.
The bigger picture now. Keep expanding out.
That's right. And therefore, we're kind of pushing the boundaries of what our brains are capable of.
Can you explain what string theory means? I don't know. Like, it's supposed to be like the smallest, the lowest common, or the tiniest common thing.
That's right. So, we all, learned in high school at some point that matter, if you take any piece of wood, you cut it in half, keep cutting it into smaller pieces, sooner or later you get to molecules. The molecules are made up of atoms. The atoms, we learned, have these little electron particles swirling around the center, which is called the nucleus, which has neutrons and protons inside of it. And perhaps you also know that inside neutrons and protons are quarks, right? So the conventional picture is that these ingredients are little tiny dots. They don't have any inner machinery inside of them. The idea of string theory, and I underscore this, is an idea. We do not know that this is correct. But if you take an electron, according to string theory, and look deeply inside, you would see something else. A little tiny filament, a little tiny string-like filament, and that's why it's called string theory. And that filament can vibrate in different patterns. And the idea is, when the string is vibrating in one way, it is an electron. When the string is vibrating a different way, it is a quark. Vibrating at another way, it's a photon, a particle of light. So all of the particles making up reality are now unified into one rubric, one idea. They all arise from the different vibrations of the string. So in a kind of poetic way, the music played by these little tiny strings results in all of the rich structure we see in the world around us. That's the idea.
Why string, though?
Yes.
Why did they come up with that? Like, why did they say it would be a bent string? And if it's a bent string and nothing is smaller, couldn't you theoretically cut it in half?
Yes. So what would you get if you cut a string in half? No, it's a good question, right? Well, it's kind of like, if you have an earthworm and you cut it in half, you still have an earthworm. And the idea here is that at least in one formulation, you cut a string, you'd still have string. You wouldn't find anything new and surprising. No new ingredient. Now, having said that, these ideas are at the cutting edge, and there are people investigating your question who are suggesting that the math maybe is telling us that there is something finer, and that the string itself is just a stepping stone, and there is a deeper ingredient yet to be found inside.
I don't even know how they incorporate math into that. Like, that's, to me, is like to what you just talk about, we can visualize it, and okay, I understand exactly what you're saying.
We can visualize string.
A piece of string inside a ball or something.
We're still in.
Yeah. But the second it starts, it turns into equations.
Right.
It's gone.
That's the tricky step for many people, because what is math? Math is really just a language that many of us are less familiar with than ordinary natural languages, English or French. That's all that it is. It's a language that's optimally suited for analyzing a certain class of problems. Now, in this case, how do we see a string in the math? Well, it's actually not all that hard to think about. If you have an ordinary string on a guitar or violin, you pluck it, it gives a certain note. But it also has certain overtones associated with it. Right? When you pluck that string, there are a mixture of notes, if you will, that are all coming together to yield the sound of a violin. Each of those different notes is a different frequency of vibration, and we have equations that tell us what the frequencies of vibrations of these strings would be. And that's how we see that it's a string. We see a certain pattern of vibrations, and we're like, that pattern, that's the pattern of a vibrating string. And does that help at all? I don't know.
Yeah, because that can be turned into some type of numerical value.
Yes,
I gotcha.
That's right. That's right.
Yeah, a frequency.
Yeah.
And when you talk about tearing the fabric of space-time, what does that mean?
Yeah, so this is work that I was fortunate to be involved with a number of years ago, where you see in Einstein's theory of general relativity, it's called, which is this theory of the force of gravity. Einstein taught us that space can curve, it can warp. You can think of sort of space as almost like a rubber sheet, going back to that two-dimensional version that's not as satisfying, but well, let's just use it because we can wrap our minds around it. So, you imagine you have a big bowling ball on a rubber sheet. It kind of curves the sheet. Similarly, the sun curves the space around it. But here's the thing. In Einstein's approach, space can bend, it can warp, but it can't rip. In Einstein's equations, if space were to rip, the equations break down, the universe grinds to a halt. That's not something that we expect could happen. We reanalyzed that issue of the tearing of space in this more refined set of equations that come from string theory. And we found that in this refined approach, space can tear. It can rip apart and reconnect in a way that doesn't cause the universe to grind to a halt. The math just smoothly sails through this tear in the fabric of space. No catastrophe at all. So it was a kind of surprising result. Nobody anticipated that this would be the new repertoire of potential behaviors when you go beyond Einstein's approach.
Wow. I love what happened. Like, what happens at that moment? Like, is it just like a chalkboard and they'll say, oh, that's it?
In terms of how we found it, or in terms of no, it really was. I was actually at the Institute for Advanced Study in Princeton when we were doing this work some years ago, and it all boiled down to an equation, a mathematical equation, and we had been working months to get this equation, and literally we were applying it to an example where if the answer came out to be 12, it's not a joke. If it came out to be 12, that meant the fabric of space could tear, and any other number it wouldn't. And we had this computer program that was ready to go, and a friend of mine had written the code. It was Friday when we were done and ready to go. He was going home, and we said, look, can't you come back tomorrow morning? Yeah, seriously. I said, can you come back tomorrow morning? We've been on this for months. He's like, no, I don't work on the weekend. I was like, are you serious, man? We're like on the verge of it. He says, look, you get me a 6-pack, and I'll be there. So
took a 6-pack.
This guy Paul Aspinwall is now at Duke. So we got him the 6-pack. He came in and we ran the code, and it didn't come out 12. It came out like 3.999 or something like that. And I was like, oh my God, all these like months of work and it's down the drain. But then we realized 3.999, that's like really close to 4. 4 kind of divides 12 by a factor of 3. Maybe we lost a factor of 3 in our math. So we went through all the equations painstakingly. Goodness gracious, we found that we'd made an error of a factor of 3, put it back in, ran the code again. It came out 11.99999, which is 12 in computer speak with the round-off errors. We showed that the fabric of space could tear.
Oh my God!
What does it mean to tear, though? Like, for the fabric of space to tear? I mean, I know what a rip is, but like, how did?
Literally, yeah. I'm talking about the same thing.
And what causes it to rip?
Well, there are processes in string theory where that is what they do. So in Einstein's general relativity, the fabric can stretch or warp based upon the presence of matter or energy. And what we found is, just like with an ordinary piece of material, if you warp it or stretch it far enough, it will tear. The same thing can happen with the fabric of space, fundamentally changing its shape by virtue of a tear and allowing it to reconnect.
So what would do that? Like a black hole?
Black holes, we think, have the capacity to have that kind of effect on space, but we don't understand black holes well enough. Yet that's right at the frontier. So deep in the center of a black hole is something we call a singularity. You may have heard that word sometimes brought up in cosmology and in black holes. And singularity is a euphemism for we don't know what the hell is going on. That's all that it means. It means that the equations are breaking down, and we need to find more sophisticated tools to understand what's happening. And right now, there must be, 400 people around the world that every single day are thinking deeply about what's happening in black holes, what happens at the edge. There's a lot of controversy that's been stirred up recently. So I don't know. Black holes may be this kind of beast that yields other kinds of rips in the fabric of space, but we don't know yet for sure.
Man. I've really had enough of the speed of light. I'm tired of it. Just enough already. They're like, it's 186,000 miles a second. Enough with it. I bet you there's something faster. They keep saying no.
Well, there was an experiment you may have heard of where they had some neutrinos. That little tiny particles that were leaving the Large Hadron Collider in Geneva, traveling through the Earth to a detector in Gran Sasso in Italy. And the initial measurement showed that the neutrinos were showing up 60 nanoseconds earlier than they could have, even if they were traveling at the speed of light. They were traveling faster than the speed of light, according to the measurements, arriving in Italy a little bit early. Now, when we heard that, we said, no, that can't be true. I mean, one of the quick ways you knew it couldn't be true is nothing arrives early in Italy, right? So that's from the get-go, right there. But more scientifically, there is a mountain of experimental support behind Einstein's special theory of relativity, which says that the speed of light is the speed limit. So one little measurement would never convince us. We would need 100 measurements confirmed by, 10 different research groups around the world before we'd say, wow, maybe there's something to this. So all of us, well, most of us, came out and said, this can't be right, or we're not convinced of this. And a little while later, the research group did find a little error in their equipment, a faulty wire, which when corrected, showed that the neutrinos were not going faster than the speed of light. So based on everything that we know today, the speed of light does still seem to be the limit for how fast something can travel through empty space.
It just seems like there's a simplistic way to get around that. Like if you're traveling at the speed of light, you throw a ball in front of you. The ball is literally traveling faster than light.
So you would think.
You would think,
based on your Newtonian intuition that came from being able to eat that antelope in the savannah.
Exactly.
Right? Now, that's actually the beautiful thing, because what Einstein showed is when you throw that ball from that train that's going, say, really near the speed of light, normally you'd say to yourself, well, how do you get the speed of the ball? Well, you take the speed of the train plus the speed at which you threw the ball, add them together. And that gets the new speed of the ball relative to somebody watching this, say, from the ground.
Right.
And Einstein says that reasoning works at low speeds, but it fails, completely fails at high speeds. There's a new way of combining velocities that comes into play, which doesn't just add them together. It adds them together and then corrects it by another factor, which always ensures that the combined speed is less than the speed of light.
But then the ball would never be moving away from you.
Nah, it depends on your perspective. So for the person on the train, the ball is moving away from them at a speed of maybe 100 miles an hour. Right. Let's say you're Mariano Rivera or something. You're throwing the baseball. It's going away from you at 100 miles an hour or so. The person on the ground watching the ball does not see its speed to be your speed plus 100 miles an hour. They see it to be less than that in a manner that always brings the total under the speed of light. Now, this is not just something weird about speed and, something that tickles the brain, because what is speed? Speed is a measure of how far you go divided by how long it takes you to get there.
Yeah.
That means it's a measure of space, how far you go, divided by a measure of time.
Yeah.
So what Einstein is telling us is that space and time don't behave as we would think based on everyday experience. Space and time have weird, unexpected properties. That's what he showed us in special relativity.
It's easier to grasp it thinking in those terms than just speed.
Yes, exactly. Because, when you hear about speed, you're like, well, that's just sort of, weird and curious, but who really cares that much about speed per se? But when you talk about space and time, look, everything we do, everything we think, everything we experience takes place in some region of space during some interval of time.
Right.
So if space and time are not behaving as you would think, that means reality is not behaving as you would think.
I got a couple questions. Where are you at with God?
Well, you know,
he's sitting next to him.
A few things. Where are you at with God and other life out there?
Well, you know, for God, my view is that there may well be a God, right? I have no evidence to convince me that there is. All of my understanding of physics suggests that that's all that we need and to understand at least the nature of the physical universe. But that doesn't prove there isn't a God out there. So my view is if what we are doing as physicists is, say, working out God's laws in some secret way, I'm thrilled to be part of that journey. That's a pretty deep thing to do.
Yeah.
And if there is no God, as I suspect there isn't, and all we're doing is working out the laws of physics that brought the universe into existence and govern its evolution, if that's what we're doing, I'm happy to be part of that journey. So from a day-to-day perspective, it doesn't really affect what I do. Now, from the perspective of other life out there, you know, that's one of those very difficult questions for a scientist to answer because the only way we'll know is by encountering that other life. Now, there are all these people who talk about making estimates of the likelihood of life being out there, but all those estimates are based on things that we just fundamentally don't know. Sure, we can now gain some insight into the number of planets that are out there, the number of planets that are similar in a sense to Earth in terms of conditions that would be hospitable to our form of life. But we don't know how life really gets started. The raw material seems to be ubiquitous out there to give rise to our form of life. What sparks life to get going? That's still an unknown for us, and that's why it's difficult to judge. But if you're asking me just sort of in a gut, completely informal sense, do I think there's life out there? Yeah, I think that there is.
A lot of it, too, right?
If there is any other life, I suspect that there is a lot.
Right. Yeah.
I have a Lightspeed question.
Yeah. You love this Lightspeed.
I really do, because it's the two things interest me about it. Like, first of all, when you're traveling Lightspeed, aren't you seeing what's behind you as well?
Well, you can't actually travel at Lightspeed.
But if you could, theoretically, wouldn't you see what
Well, here's the thing. Sometimes if one asks a theoretical question, the reason why the answer seems so confusing is because it's a perspective that you could absolutely never have in principle. So what I'd say is if you go very, very close to the speed of light, you can look out at the world and ask yourself what you would see. And I've got some fantastic animation to show you what you would literally see. I can't obviously do it here on the radio, but the world would look slightly strange. It would look kind of curved and warped, and features of it that are completely unexpected based on slow speeds would start to become readily apparent. You know, if you watch a taxi cab going down, say, Fifth Avenue near the speed of light, right? What would that taxi cab look like? It would be shrunken to a very, very thin width, and it would be twisted as it's going by. So, it would, you know, an ordinary taxi cab, what is it, 10 feet long? It might be 1 inch long as it's rushing by you, because that's what happens to space at high speeds. Again, that connection between speed being space per time, that's what would happen. And if you were to look at a clock inside that taxi cab as it's rushing by, that clock and everything inside that taxi cab would be ticking slowly. People in the taxi cab, their eyes would be blinking slow. Everything goes slow because time itself slows down at high speeds.
That is so...
Is there like a way you can kind of visualize with the speed of sound when you get that Doppler effect?
Yeah.
With that, is there any kind of similarity between that?
You can, but it doesn't really bring out the weirder side of things. So it is the case, as you're saying, you know, if an ambulance is rushing toward you, it goes, that kind of thing. Right, exactly. So that's the Doppler effect, which is how the wavelength of a signal, a wave, is affected by the motion of the source. That happens with light, too. So if an object is coming toward you, it'll look bluer. If it's rushing away from you, it will look redder. That's the analog of the siren sound sort of going up and down in terms of the pitch of the siren. But the weirder part, though, is the speed, as we're talking about, not the frequency of the waves, but rather the speed that the signal is traveling. And that is different for light. That's a strange feature that's very hard to grasp, and you just ultimately have to accept it. Because if you were to say to me, why is it that the speed of light is constant? Why is it that nothing can go faster than the speed of light? At some deep level, I have to tell you, I don't know.
Because that's the way
That's the way it is. I could imagine a universe.
Them's the breaks.
I could imagine a universe where it's not the case. Right. Logically, I can imagine a world where Newton got it right. Late 1600s, he figured it all out, and that's all that there was. And everything behaved according to intuition. That would be a kind of boring universe, certainly for a 21st century physicist like me, because nothing would have happened in the last 500 years or something. So we look to Einstein, and I say, I thank Einstein for his insights, because it made the world so much deeper and richer for us to figure out. And who doesn't get totally bowled over by time slowing down or space crunching at high speeds? It's spectacular. But did it have to be that way? Hard for me to say that it had to be that way. But it is that way.
What are some of the things we'll be able to do with the knowledge we have now? Let's say in the next 20 years, some of the things that you think will be possible.
Well, I take a step back and just, it's good to remember that, Einstein's ideas, those ideas of quantum mechanics, which is, the physics of the small things, electrons and molecules and atoms, that has allowed us already to create almost everything in this room, right? So personal computers, cell phones, all manner of medical technology, anything with an integrated circuit comes from quantum physics. Without quantum physics, you wouldn't have all that stuff. Some have estimated something like 35% of the gross national product comes from quantum mechanics. So already, fundamental physics has, in a profound way, changed our lives. Where will these discoveries lead us in the next 20, 30 years? I don't know. And I'm sort of excited to say that, because...
You have any hunches, though? Or?
Yeah, well, what are we trying to figure out these days? So with string theory, we're really trying to take Einstein's ideas and push them further and really understand the basic structure of space and time. If these ideas are correct, could it be that in the distant future, I'm not talking 20 years, I'm talking, maybe 20,000 years, would that allow us to manipulate space and time? Maybe. I mean, that's the rhythm of science. You understand something deeply, then you start to use your understanding to manipulate it. I don't mean in some dark way, but you just take control over it. Now we can manipulate the motion of electrons, and that's why you have your cell phone. Well, could we ultimately use our understanding to manipulate space and time? Would that yield to fantastic space travel or time travel? In the wild imaginings, yeah, I could at least envision that as a possibility.
And what is they discovered the God particle? What exactly does that mean?
Yeah, that's this thing called the Higgs particle, the Higgs boson. And that's a particle that was emergent from the equations in the 1960s. But we didn't know if it was true or not. Again, it was just math. And then a machine was built in Geneva, Switzerland, and this little tiny particle that the math said should be there is there. Now, what does it do? This is a particle whose corresponding field, all particles correspond to fields that fill space in this case. And the Higgs field, we believe, is a kind of cosmic molasses, filling every nook and cranny of space. So that as fundamental particles like electrons or quarks, they try to move through space, they rub against this molasses. That kind of gives them a resistance that we consider to be the mass of the particle. So why does an electron have heft? Why does it resist when we push on it? Answer, according to these ideas, it's rubbing against this cosmic molasses, the Higgs field. Now, this was math in the 60s. I learned about it as a grad student in the 80s, and for months I thought it was real. I didn't know it was hypothetical because the professor was already so convinced it was right. He didn't even qualify the description when he was teaching at the blackboard. But it was only in 2012 that we got the first solid evidence that this is really real from these collisions at the Large Hadron Collider, and now there's a basic consensus that these ideas are correct.
So you're saying the resistance that you get from mass trying to move mass,
yes,
is that?
That's right.
Wow.
Without the Higgs field, the idea would be that if you pushed on any object, it would be massless. It wouldn't resist it at all. It would just go flying off at the speed of light.
Right.
The reason why light still travels at light speed is it can go through the molasses without interacting with it at all. That's one of the beauties of this molasses. Light just goes through it, like a hot knife through butter, right? Even more smoothly, it just goes right through it. But other particles, like the electrons or the quarks, things of that sort, they don't go through so smoothly, and that resistance is why they've got heft.
Interesting. Yeah.
And what is the...
I feel it when I do this.
Yeah,
that's it. That's right. That's right. Now, let me just point out one little subtlety. Little subtlety. Sometimes people say the heft of ordinary objects, therefore, like that book or a coffee cup, therefore also comes from the Higgs field. That's not quite true. Because the objects like protons, which are collections of quarks, there's an additional source of their heft that comes from the way the quarks talk to each other, certain interactions. It's called the strong nuclear force. The name doesn't matter much. But that's where the heft of ordinary conglomerates come from. But the fundamental constituents is what I'm talking about. That's where they get their heft from the Higgs field. That's a footnote.
Damn. A little footnote.
Yeah.
Yeah. I'll tuck that away.
Yeah. Bring that up to one of your next guests.
Well, we've got a dog trainer coming in there. Awkward. Long day to book the dog trainer.
Oh, my God. No, I love this stuff. I really do. My whole life I've been
it just blows my mind.
Into it. It's
the whole
amazing.
Thing.
What percentage of gravity on Earth are the astronauts experiencing? Are they? I've heard two different things.
Well, if they are in free fall, then they aren't experiencing anything. So one of the insights of Einstein is that anybody who is in free fall, you jump out a building, right? You're out there in space and you're in orbit, which in essence is an object that's free falling around the Earth. You've canceled out gravity. This is called Einstein's equivalence principle, that you can cancel out gravity by undertaking a certain kind of motion, which is basically a free fall motion. If, however, a rocket out there is accelerating, then the people will feel themselves pushed against the seat or against the floor, and they'll feel something equivalent to gravity. Now, if someone's not in free fall and they're literally hanging out there, then the amount of gravity they're feeling is pretty close to what we are experiencing here on Earth. Obviously, it depends how far away they are, but I'm talking if they're on the order of a couple hundred miles away, the Earth itself, what is it, about, 8,000 miles in diameter or something, so 4,000 in radius, so 100 miles is not that far.
It's gonna grab you.
We're already, right here on the surface of the Earth, pretty far from the center. And that's what dictates how much gravity you feel. How far are you away from the center of the object?
So the movie Gravity was a comedy to you.
It's funny. I was just, with all the Oscar stuff, I was asked about this so many times,
right,
about the sort of science gaffes in Gravity. And my view is, I don't really care as much about that. I go to the movies to let go of all that. You talk about, is physics always with you when you're making the left turn in the car? Do you feel the centrifugal force? It is. So I like to sit there in the movie and let it all go and just enjoy what's happening. So I'm not sitting there like with my pad of paper and say, oh, they got that wrong, they got this wrong. Here's what does bug me, though. If a movie breaks the rules, there you go. Here's the thing. If a movie breaks the rules, right, and they do it consistently, so I buy into this new set of rules, I'm fine with that. But if at the last minute, like a plot device suggests to them that they should now buy into a different set of rules that contradict the other rules that they had me buy into at the outset, I don't like that. Then I feel like, oh, come on, that's like lazy thinking. But you want to bend the rules and you do it in a consistent way, I'll go with you. I'll go with you completely.
Buzz Aldrin said that the way they moved in space, colliding, all that stuff, he said was fairly accurate, the way things got banged around up there.
Yeah, but I mean, there are other things. Again, I wasn't sitting there like critiquing as a thing in my mind. Because there's like a key moment when like George Clooney's holding on to, I don't know, it was a rope or something. And Sandra Bullock is like trying to keep him from like flying out into space. In reality, once that thing pulled taut, there would be no additional force that would be causing him to continue to be pulling on it. And therefore, that was a kind of a weird moment. But, you can justify it in your mind. If the entire object was spinning around like a merry-go-round,
then it would want to fling them off.
Then it would want to fling them off. So that's how I would justify it in my mind. They didn't show us the spinning, but it was really spinning up there.
It must have really been spinning. Once they
give them the benefit of the doubt.
He definitely could have made it back with her because once
that thing pulls taut, that's then then he basically gets pulled back in.
Let's go to Dan in Atlanta. Dan, what's up?
Hey guys, I just proved my own scientific theory. You put a physicist on the O&A show and the phone lines are wide ass open.
No, not really.
No, they're packed.
We just don't have time to go to them. They're packed. They've been packed since Brian Greene came in today.
Really? Well,
it's worldscienceu.com, by the way. He's promoting that today.
Answer me this. So you've seen this through a number of generations, right? You've seen guys that came through with you. I'm 34. So when I went through school, it was a little more similar as today than when you went through, but still wasn't like it is today. How do you keep kids interested in this stuff?
Huh?
You know what I mean? You got the pioneers of the past. You've got them into your decades. You've got them into my decades. And I keep seeing these young kids, and it's like, how do you get them interested?
Yeah, I mean, you don't mind if I take that one, guys?
No, go ahead.
You know, my view on that is, what we do wrong is we teach science as if it is a finished subject. There it is in the textbook, and you just have to learn it. That isn't going to fire anybody up. But if you teach science as an ongoing journey of discovery, a dramatic story of discovery, as we have continued to dig deeper and find stranger and stranger things, and that's where we're heading off into the future, yeah, then kids get real excited. You know, I can't tell you the number of times I've talked to a young group of kids, right, and I'll tell them something about black holes or the Big Bang or things like that, and their eyes start to open wide. They're like, whoa, wow, time slows down near the black hole, you know, the beginning of the Big Bang. And then they often say to me, wait, but that's science? And I'm like, yeah, that's science. It's not just memorizing these things that you spit back on an exam. And once kids make that transition to recognize that there's such wondrous stuff still to figure out, many of them have a very different view of science.
Yeah, if you could tell somebody that they can be part of a continuing story that's going on, of course it's better than just here's this, finish it, and report back to me.
Right, exactly.
Let's say hi to Bob in Tucson.
Hey there, Bob.
Hey, Dr. Greene, how you doing?
Good. How about you?
I'm in love with the string theory because I feel that it really fits in with the whole concept of what a lot of people might conceive as God and a higher power. And how does that kind of figure in with your thinking, and how can you relate that to the whole concept of God and being one central controlling figure in the universe?
Yeah, we sort of hit on this a little bit earlier, and my view is that physics doesn't have a whole lot to say about God, right? So we're trying to figure out the laws of physics and apply them to understand reality around us. And could God be behind it all, pulling the strings, so to speak? Yeah, it's possible. There's no evidence for that. So we keep it in our mind as a possibility, but we press on with the equations, with the experiments, with the observations to just try to push the procedures of science forward.
But what about the baby Jesus?
How does he fit in?
Yeah, how does the baby Jesus fit into all this? Thank you, Bob.
Well, I'm
go ahead. Sorry.
I'm an agnostic, and I really feel that that's kind of like the whole controlling thing throughout the universe. It's this string theory that can tie us into different dimensions and different ways of that when we die, that's not, we don't just basically get snuffed out. It's those thoughts and those things that have triggered things throughout our life that cause us to be remembered and cause ghosts and those little things that trickle throughout the universe that cause us to be our essence of what we are. Does that make sense?
I don't know. Honestly, I don't know what happens when you die. From the point of view of physics, from the point of view of physics, look, it's a pretty subtle change in the state of your body when you die. So if we're just analyzing the physics of what's going on, it's not completely obvious that something dramatic has happened.
We all are electrical creatures. I mean,
sure.
That's what basically controls our whole body is this electrical impulse that runs through us. And I just kind of feel that, that some hairy guy sitting up in space somewhere granting wishes doesn't make sense to me. But
right.
If you can kind of grasp it through physics, that kind of makes a whole lot of sense to me.
Yep, I agree. It doesn't make a whole lot of sense to me either. But on the other hand, quantum mechanics didn't make a whole lot of sense to some of the greatest geniuses of the 20th century. And it turned out to be right. So the thing is, the only ideas that I'm willing to buy into are ideas that have a strong mathematical basis, which ultimately are confirmed by experiment or observation. That's the gold standard. And all these other things that we talk about with God, and I don't even know what it means in any deep, rigorous sense. I have an intuitive feel for what people mean, but it's hard to test that kind of an idea.
Right, there's no way to figure it out.
Yeah. Now, on the other hand, if the sky was to open, and the big man up there said, "I'm here, I am God," I wonder, would I be convinced then? Part of me says, well, I guess I would. Part of me feels like maybe I'd check myself into Bellevue at that point.
Yeah.
So I don't know what exactly I'm looking for when I say, where's the evidence?
Right.
What is that thing they did with...
one truck driver.
Right.
All right. Thank you, Bob.
What is that thing they did where they had like two... It was like a quantum physics experiment where a particle was in two places
Yeah,
at
the
once.
entanglement, quantum entanglement.
Now, I'm sorry to interrupt you.
Yeah,
my question was, is that a possibility? If that's real,
yeah.
Is it possible that it could be from one place to the other faster than the speed of light?
Right. That's a deep and difficult question. It is the case that in quantum mechanics you can have a particle over here, say in Los Angeles, another particle in New York, such that you measure the particle in Los Angeles and it seems to instantaneously have an effect on the result of a measurement on the particle in New York. They're 3,000 miles apart, but yet what you do on one seems to have an effect on the other. Einstein himself called this spooky action at a distance. And he said, it can't really be that way. But experiments seem to establish that it kind of is that way. And you might say, well, there you go. You've now done something faster than the speed of light. And actually you haven't. Because there's no information that you can transmit from one place to another faster than the speed of light. Rather, it's a correlation in their behaviors by some weird quantum effect that we understand the math of it completely well. So I don't want to leave you a sense that this is a mystery. We understand this. We do experiments with this. We use it. But from the fact of relativity, when Einstein describes it, it's really no information, no signal can go from place to place at faster than the speed of light. In this case, when you analyze it closely, no information would go from Los Angeles to New York. You couldn't say, sell Yahoo or sell Amazon stock. There'd be no way for that information to be transmitted through this influence. So in a sense, relativity survives by the skin of its teeth. But again, this is at the cutting edge, and people are still trying to figure this one out. And maybe, if you have me back at some point, I'd say, you know what? You were right. We now understand it better, and there's a real issue.
Only because it seems like, how could they, I know my mind can't grasp.
Can you explain this one a little further, Jimmy?
Not really. I think Brian would probably be better than I would. I think if you have two particles in two different locations, like you said, one reacts to the other in a way, but you're saying there's no information being transmitted.
Yeah, I can tell you why. In maybe a minute. So one of the weird things of quantum physics is we learn that the best you can ever do in an experiment is predict the probability of an outcome. That's the big break of quantum physics. Newton says, you predict how things will be. Quantum mechanics says, no, Newton, you are a little bit wrong on that. You only predict 30% chance of this or 40% chance of that. So here's the idea. You can have two particles in Los Angeles and New York set up in the right way where there's a 50-50 chance that this particle will, say, be red or blue. 50-50 chance that the one in New York will be blue or red. Okay? So it's a chancy thing. You measure the one in Los Angeles and say you find it's blue. The one in New York necessarily then will be red. But that's weird, right? Because how could doing something in Los Angeles affect the color of the one in New York? But that's what quantum mechanics says happens. But now, how would you transmit any information with that? Well, let's say you had many of these particles in Los Angeles and New York. You do a bunch of measurements in Los Angeles, red, blue, blue, red. Maybe it comes out. The ones in New York then will be the opposite, blue, red, red, blue. But there's no information in that. It's just a random list of colors. It's only when you bring the two lists together from Los Angeles and New York and compare them that you say, oh, wow, every time you got red, I got blue. Every time you got blue, I got red. But that comparison has to be done slower than the speed of light. How do you get the two lists together? You get on the phone, you send an email. That communication is slower than light speed. And only when that communication happens do you go, wow, something weird's happening. You got red, I got blue. You got blue, I got red. It's only in the comparison.
That's wild.
Right. So, because I was thinking you could absolutely transmit information through those changes, but to then coordinate what they're each doing slows you down.
That's right. It's only the coordination, ultimately, which shows the information.
But if, and again, I'm just trying to grasp it. Like, if the coordination shows the information, doesn't that mean that the information is there even without us knowing it?
That's a good point. It's a tricky one, and that's why people are still struggling with these ideas. But as far as we can tell right now, it's only when the information can literally be extracted that you consider the information having been transmitted. So you might say it's sort of latent information. It's kind of there. But even though it's there, if you can't extract it, then we'd say that the information hasn't been transmitted. Only when you bring the list together can you extract it, but that's a slower than light procedure because of the comparison.
But does it happen where, like, the things where the one will happen in Los Angeles and it won't affect the one in New York, or does it always affect it?
No, you have to set things up in a very careful way for everything we're talking about to happen. So some people say, well, okay, you set it up to do that. What's so surprising? I'm telling you, it is surprising. I don't care what you do to set it up. If you're going to tell me that there's a 50% chance that this guy is red and blue, 50% chance that this is blue or red, and you measure this one, and then this one now is 100% blue because that one turned out to be red, whereas before you did your measurement, it was a 50-50 chance, that blows my mind right there.
Wow.
I don't care what kind of a magician or how you set it up. That is amazing. And that's what quantum mechanics says.
Can I have one more question about what about these whatever they were? Were they these? I guess they were whatever photons, something small. They changed patterns when they were being observed.
Yes. So that's a common occurrence in quantum mechanics, that the act of observation has an impact on the thing being observed. Again, it's a new idea in some sense because in Newton's physics, you could be very gentle when you observe something and that way disturb it minimally if you're a very good experimenter. But quantum theory says that no matter how delicate you are, an observation will have some impact on the thing being observed. So take those particles you were just mentioning, the one in L.A. that was 50% red, 50% blue. When you measured it, it came out 100% red, say. So you changed its pattern, its probabilistic pattern. It was 50-50 before you looked. Then it was 100% zero after you looked because it came out red. And once it's red, it ain't going to be blue. So that's an effect of the observation on the state of the object itself. And that's a kind of ubiquitous feature in quantum reality.
Is it changing because you observed it, or was it always that way, but until you observed it, you wouldn't have known?
There it is. So that's what Einstein asked. That is exactly what Einstein asked. And Einstein believed, that it always was red.
Right.
But your description was just a little bit incomplete, and therefore you thought it was red or blue. That was Einstein's view.
Yeah.
But amazing experiments that have started in the 80s and through to today have pretty much shown that Einstein's view of that was probably not right.
Wacky-haired bastard.
It seems to be the case that the object really is, as far as we can tell, in a mixture of these distinct possibilities and only snaps out to a definite reality upon observation.
It's almost the tree falling in a forest.
In a sense.
Nobody hearing it.
Right.
Yeah, that's interesting. I love it.
We got our next guest outside the studio.
I got to tell you, Brian Greene, thanks so much for coming in.
Greene, by the way, sorry, BGREENE on Twitter. Larry the Cable Guy is outside the studio showing us his fat stomach.
Showing his gut.
See, that's